In this section, we talk about the visually symmetric problems. What this problem comes from? This problem have some special shape. Let me give you the previous example. This one. In this example, we have only visually distributed loadings, such that the whole deformation, the deformation of the whole plate is symmetric. So the most important point is the deformation and the stress and the displacement all are independent of the value of theta. The physical quantities only depend on the variable r instead of theta. Okay, this is the key point about visually symmetric problems. Later, we will also study another two visually symmetric problems. For example, like this. Okay, like a water pipe line. Outside the pipe line, there is some earth pressure. Okay, soil pressure. Okay, you bury the water pipe line under the ground. There are some water pressure, soil pressure outside the pipe line. Inside the pipe line, there are some water pressure. Okay, and these kind of pressures are visually symmetric. So since that the pipe line itself is circular, is in circular shape, so the whole problem is visually symmetric problem. Another problem is like this, like a steel ring, okay, subjected to some deformation, subjected to some pressure outside, okay, but inside the steel ring there is some rigid core, okay, buried inside the circular ring, such that in the inner boundary there is no displacement. Okay, it cannot move, fixed. Such kind of problem is also visually symmetric. Okay, let us begin with the general calculations. The most key point, the most important point is that the stress function here is not the function of theta, it is only a function of r. So we can assume that phi is phi r. And then we put this simplified stress function into the biharmonic equation. The Laplacian here is written in this way, but because phi r is not dependent on theta, so the differentiation with respect to theta is not useful. So we just cancel it out to write it delta the Laplacian equal to the triangular operator like this. So in this kind of reasoning, we can start it from the biharmonic equation and end up with this form. Okay, these two triangle operator, each triangle operator equal to this form. But see, such kind of equation have been solved before. Okay, in what place? In here. Okay. Problem 2. Okay, so we have already solved the same problem in the previous section there. Okay, that is this problem. Okay, this is a visually symmetric problem. So the mathematical calculations are almost the same. Now we get back to here. Phi equal to phi r. We put this into this form, and then let phi r equal to ra. After some calculation, we will understand that the result will be like this, and then we get two roots, a equals 0 and a equals 2, and then we get this general solution. We have already obtained such kind of solution before. Huh? Remember, a plus b squared plus log r c plus d Let me show you. We had already obtained such kind of, yes, here, FR, A plus B square, BR square plus log R plus C plus DR square. So here, we had already calculated such kind of stress function before, okay? So we can cut it short. We get this stress function. Now, remember, in the last section, we said that we can argue that the constant D can be equal 0, right? And by that time, we said that we will explain such kind of reasoning later. Okay, this is the time now. Okay, let us look in the detail how this constant can be set to be 0. Okay, we get this stress function, so we get the stress component by such kind of formula. Okay, without difficulty. We have BCD, BCD. Okay, there's no shear stress because it is a radially symmetric problem. And from this stress function, these stress components, we can use the Hooke's law, okay, the stress strain relation to compute the strain components, right? We just put sigma r here. Just put this here, okay, and sigma theta, just this one, and put it like here, okay. And after some reorganization of the term, you'll see here, we can rearrange our terms like this. Okay, we rearrange our terms like this. So having the stress function, we can calculate the stress and strain. More important, we can calculate the displacement. Okay. We use two equations to solve two unknowns. Let me show you. Here we have three strain components, but this one is satisfied automatically because we are solving a radially symmetric problem. So the only two conditions we should consider is this one and this one. Using epsilon r equal to this function and using epsilon theta equal to this function, we have two equations. Two equations to solve for two unknowns. What unknowns? Let me show you. Here, U and V are the two displacements we want to have. Okay, so we have already load the function for epsilon r and epsilon theta. So we get two equations, and we want to solve U and V. Okay, two unknowns. Okay, by solving this equation. Okay. Epsilon r equal to partial u partial r. Epsilon theta equal to this one. Okay, u over r plus 1 over r times partial v partial theta. Okay, but now epsilon r equal to this form. This is the function here. We just copy this formula to here. By the same way, we can copy the epsilon theta, this formula to here, okay? So we can integrate these two equations to obtain u and v, okay, later. We first try to integrate this equation to get u. See here, partial u partial r equal to this function. This is a function of r. So we can move this partial r here to carry out the integration. Okay, u equal to this one integrate to dr, right? Dr, right? And we have an arbitrary constant here. Understand? Okay, and the integration is easy. This is a constant term, so we get the integration is direct. We have a r. This is 1 over r squared, so the integration is 1 minus 1 over r. Here, this is a constant term, so the integration gives you r here. This is log r, the integration will give you r log r minus r. Okay, now we have already obtained u. Okay, now we can put the the function this function u inside this equation, okay, to solve for v. Understand? We put this function into this term, right? Okay, this term. So we just do it. This term still unchanged, okay? We just copy this term here. And this term now replaced by this term. What is this term? This term is r, u divided by r. This u divided by r is this one. So this one divided by r is this one, okay? This finishes the substitution. We substitute the formula here into here. Another one, and on the other way, f of theta equal to this one. This, where this formula come from? This formula come from the formula in the last page, previous page. Okay, this one, right? It is also equal to this term. Okay, so by using this relation now here, this is a function of r. This is a function of r. So this is a partial v partial theta. So we try to combine this term with this term, okay? So we write it like here. So the whole equation, this one, this part will be written like here, okay? The whole equation can help us to solve for partial v partial theta. Understand? And then we combine this term, this part and this part to become this part. Understand? Okay, let us do the combination. When we combine it, we found that this term and this term can be cancelled out to each other, and this term and this term can be cancelled out to each other, and this term and this term combine into this term. Okay, this term and this term combine into this term, and this term and this term and combine into these terms. Okay, and this term is written right here. Okay, once we do this, we can simplify the result in a further way. Okay, we cancel out this part and this part, okay, to get this one, and finally we end up with a constant 4 here. Okay, so the result is quite neat. Okay, quite clean. Okay, it is quite simple. So this one is written right here, this one written right here. So we have R finally. Okay, R, why? Yes, because this R will come from here, because we move this R to here. And then we cancel this R with this R to get C1. So we end up with partial V partial theta equal to a linear function of R. So a direct integration with respect to theta will give us the function v. Okay, we integrate this term and this term, the left hand side and right hand side, with respect to theta, will give us this result. If we integrate this term with respect to theta, we get v, and this one will become here. But see, theta and r are independent to each other, so the integration can be carried out directly, and this term will become like this, and this term become like this. Now, come to the main point. See, one more thing. The integration here should have a integrate. See, every time you deal with the indefinite integral, you carry out the integration, you have a integration constant. Here I didn't put an integration constant because I forgot. So please put it back. Part C2 here, there should be an integration constant, but it doesn't matter. Just a constant. It's not very important. Okay. The important thing is, see, V is the displacement. So the displacement for a visually symmetric problem should not depend on theta. It should be dependent on the function on the independent variable r only. Okay, so v equal to vr but not theta. Okay, this is a displacement in the theta direction. Okay, but it will not be depend on the independent variable theta. But how come we will have the result here? Okay, so this direct calculation will lead us to this unreasonable result. It tells us that V depends on theta, so V is not visually symmetric anymore. So the only way we can resolve this difficulty is that we should let D equals 0 and C1 equals 0. Understand? So finally, we know why the constant D must be equal to 0, because if it is not equal to 0, then the displacement V calculated from the stress field and strain field will not be visually symmetric again. So D must be equal to 0. Okay. So, of course, we should put a constant C2 here. So finally, V not equal to 0. V is equal to a constant C2. C2 is a constant of integration. But it is not very important, not very not very significant, because V is equal to 0 means that there is no displacement in the theta direction. If V equal to C2, a constant, what it means? Means that in the theta direction we have a rigid body rotation. Okay, means that even though you rotate the circular wing with a rigid body rotation, it doesn't change the deformation. Okay, this is a trivial result. So you can put V equal to C2 instead of V equals 0. No matter how, we had already find out all the things we want to have. So for a general visually symmetric problems, we have the stress field like this, because D equals 0, right? Let me show you. See here, the stress component is like 2b plus c over r squared plus d here, but d now is equal 0, okay? And this one equals 0. So we have sigma r equal 2b plus c over r squared only. And sigma theta equal to 2b minus c over r squared. Okay, this is the result where we had obtained. Okay, in the same way, the strain component should be written like this without the constant d. Okay, for the displacement, we had already obtained like this before. U equal to this one. Why? Because U equal to this one, but D equals 0 now. D equals 0 now. So we have this one copy to here. Okay. So this is the final result for the whole physical quantity, whole set of physical quantities for visually symmetric problem. For any visually symmetric problem, the stress field is written here. The strain fields are written. The stress fields are written here. The strain fields are written here, and the displacement field are written here. Okay. So it seems pretty okay. Not yet, please, because in this stress components and strain component and displacement, we have some arbitrary constant inside, right? B and C, B and C, B and C. So we need to use some boundary conditions to determine these unknown constants. Okay, let us look at example 1. Okay, we have already explained this example before. A circular section, maybe a water pipeline, the cross section of a water pipeline buried under the ground. So outside we have the soil pressure, inside we have the water pressure. Okay, this condition is written like here. B R equal B, we have the pressure like this. R equal A, we have the pressure like this. I means the internal pressure. O means the outer pressure. Okay, this is a traction boundary problem because all the boundary conditions are written in terms of traction. Okay, we call it the traction boundary conditions. The problem is a traction boundary problem. Okay, now we put the R equal B condition inside the stress field here. Okay, we have the sigma R here. We put R equals small b and R equals small a to calculate the outer and inner pressure. Okay, like this. So once we do this, but be careful. I have do some miscalculation. Okay, I make some mistake here. This is not theta theta. This should be r. Okay, please make the modification. Not theta theta, r, and this minus sign become a plus. Okay, plus. Okay, and then so since I have already I have made some mistake here. So you should not follow my calculation in detail. But I tell you that it is only a algebraic equation for in what level? Junior high school level. Okay, when you were studying in the junior high school, when you learn mathematics, you know how to solve for one set of two algebraic equations. Okay, two equations for two unknown, B and C. Okay, so solve by yourself because your teacher here makes some mistake. Okay, this should be sigma r, this should be plus sign. Okay, solve by yourself, and you will get the result about B and C. And then after you get B and C, you can put it back to the formula here. And then you get the stress field and the displacement field, and you get everything. Okay, do it by yourself. In example 2, we have a circular wing with a rigid core buried inside. So because we have rigid core here, there's so in the inner boundary we have no displacement at all, right? Because it is fixed. We have no displacement at all. And in the outer boundary we have the outer pressure. So this is a mixed type boundary conditions, because in the outer boundary the boundary condition is written in terms of traction, right? This is the stress. And in the inner boundary here, the boundary condition is written in terms of displacements. So it is not a traction boundary condition. We call it the mixed type because we have some traction and we also have some displacement. Okay, we mix them up together. But the process to solve for the constant B and C are almost the same. Let us take a look. For the first condition R equal B, we have the condition here. Remember, sigma R equals sigma O. So sigma R equal to sigma O at the left hand side, and the right hand side 2b plus c over little b squared, because in the outer boundary little r equal to little b. Okay, if you put like this, sigma r equal to sigma 0 equal to 2b plus c over b squared, then you get the first boundary condition here. Okay, for the internal boundary, we have r equal a and u equal 0. So we use the formula here. U equals 0. Okay, 4.4.13. U equals 0. U equals 0 at r equals small a. Put change r equals small a. Change r equals small a, and u equals 0. And then we have we can finish the second boundary condition. Okay. Here, r equal a, r equal a. Okay. So now, once again, we have two equations for two unknown. One equation, two equation, and we have two unknown, b and c. So it is a mathematical problem in junior high school level again. So you can solve it by yourself. A set of two algebraic equations, a linear equation. You can solve it for the two unknown b and c. Okay, without trouble. I have already done it for. I have already done it for you. Okay, so you follow my calculation carefully. You get c, and you get b here. Okay, maybe I will make some mistake. Find it out for me. If I have made mistake and you find out, you may have some extra points as the bonus. Okay, so solve these two equations. We can get c and b, and then after we have this, we put c and b back to the stress component. Okay. Here we have the stress component with some unknown constant. Now we had already know b and c. We just put them back, and then we will have the distribution of the stress components. In the same way, we can also do the same thing for the strain and the displacements, and the problem is solved easily. Okay.